Why does pressing one speed button on a fan cause other buttons to automatically pop up? How is oscillation achieved without an additional motor? Why does a broken ceiling fan only hum and not spin? Let's clarify everything today. The fan panel has a total of 4 buttons. They correspond to 3 speed settings respectively. The button on the far right is specifically for turning off the fan. A clever interlocking design is hidden here. When any speed button is pressed, the previously pressed button will automatically pop up. Only the colored power button does not lock. It springs back immediately upon release. Opening the casing reveals the internal structure. Each button has a small reset spring underneath. Under normal conditions, the springs constantly push the buttons upwards. Inside the fan body horizontally, there is a metal plate with a tooth slot. A small side spring continuously pushes this metal plate to the right. When a speed button is pressed, it pushes the metal plate to slide to the left. Once fully pressed, it directly engages in the slot, locking the button and preventing it from popping back. Then when another speed button is pressed, the metal plate slides and shifts again. The previously locked button is released, and the old button immediately pops back to its reset position. The power button, however, has no corresponding locking slot. Pressing it only pushes the plate to release all speed buttons. It springs back automatically upon release. 3 different colored control wires extend from the rear of the fan. After selecting the desired speed, current flows directly through the wires to the top motor, controlling the motor to operate at different speeds and deliver airflow. Normally, the fan blows air in a fixed direction. To achieve wide-range airflow, simply press the head's positioning pin. The fan will then automatically oscillate left and right to distribute air. Many people assume that fan oscillation requires a separate small motor. In reality, it's not necessary at all. The designer cleverly converts the rotational power of the fan blades into oscillating power. This is achieved through the classic 4-bar linkage mechanism. The entire structure consists of 4 movable connecting rods joined by pivot pins. The fan head internally is equipped with these 4 rods, forming a complete oscillation transmission assembly. To make the fan's rotation drive the crank, it relies on the built-in gear reduction system. The end of the fan blade shaft is connected to a worm gear. Adjacent to it is a meshing worm wheel. Below, a series of transmission gears are connected in sequence, eventually connecting to the oscillation crank. The positioning pin that controls oscillation internally contains a spring and 2 ball bearings. When the positioning pin is pressed, the ball bearings lock onto the worm wheel, rotating synchronously. Power is smoothly transmitted to the crank. The 4-bar linkage mechanism engages, and the fan begins to oscillate left and right. When the pin is pulled out, the ball bearings disengage from the meshing state. The entire transmission structure becomes stationary. The fan then maintains a fixed glowing direction. Furthermore, after being reduced by the gear train, the oscillation speed is much slower than the fan blade speed, resulting in a smooth and gentle swing amplitude, without any violent shaking. Having discussed pedestal fans, let's now examine the construction and operating principle of ceiling fans. When manufacturing a ceiling fan, the stator core is first sacked and stamped into shape. Then the starting and running windings are wound around it. The rotor shaft is precisely installed in the center of the stator core. Internal wires are connected. The stator core assembly is completed. 2 sets of upper and lower casings are attached. Wear-resistant bearings are installed. The upper casing contains the rotor core. The overall frame is assembled and fixed. Finally, the capacitor base is installed and the starting capacitor is connected. Finally, install the capacitor base and connect the starting capacitor. Tighten the fan blades and a complete ceiling fan is assembled. Many people wonder why a ceiling fan doesn't rotate on its own after being powered on. In fact, household ceiling fans use single-phase alternating current. Simply applying power only generates an alternating pulsating magnetic field. The forward and reverse forces cancel each other out, making it impossible to form a rotating torque. This type of motor cannot start on its own. This is also